Мой первый доклад по-русски, но well, so I hope that now that I will start teaching in English, as it was asked of me last time, the class size will not shrink further. Very well. Please tell me if you ever want me to go more slowly. Если у вас вопрос по-русски или по-английски, вы можете спросить по-русски или по-английски. Все хорошо? Да. The sources for today's lecture, well, there are several, but some things I recommend are, so there are the lecture notes by Ben Green online. I believe the name is Structure in Additive Structure in Set Theory. They are a bit old, so they don't contain the older, the best versions of all the proofs we will give now. So there will be differences, and I should also thank two of my students, former students, because they did a small a bachelor's thesis, more or less, on the subject of today's lecture. And tomorrow, not tomorrow, but the next lecture. We will have to decide at the end when we're going to have the next lecture. We can have it next Monday, or we can also have a lecture on Wednesday, as you prefer. Когда следующий раз? В понедельнике или в среде?
Понедельник.
Понедельник.
В среду Звонкина.
Да. Да, очень хорошо. But we will, so I will certainly speak here on Monday, but I hope that, well, perhaps later we will be able to make up for the fact that I was not here, I couldn't be here last time. All right. So, what is one of the main questions of additive combinatorics? Let A be in G, finite subset, or in general, A in G, finite, G abelian. So this is the classical setting of additive combinatorics, the abelian setting. So how large is the set A plus A compared to A? If at any point there are any questions, or I should go more slowly, please do tell me. So there are two extreme forms of behavior. So if you consider the powers of 2, the size of A is K, whereas the size of A plus A is K times K minus 1 over 2. So A plus A is much larger than A. Whereas you have the opposite extreme in the case of an additive progression. You see here what happens is, by A plus A, I mean the set of all pairs of elements of A, correct? So just to recall, A plus A is the set of all sums of two elements of A. So here what happens is that any pair of any sum of two elements is distinct. In fact, I think this is K plus 1. Sorry, is this correct? Yes, it's correct now. Yes, I think it is correct. Yes. You see, what I wrote, what I had before on the board with a minus, was just pairs of all sums of two different elements. So 1 and 4, say. And I had to divide it by 2 because 1 plus 4 is equal to 4 plus 1. No? But other than that, there are no repetitions. 1 plus 4 will never be equal to 1 plus 8 or whatnot, or to 2 plus 8. There were no repetitions. And then I added k, which was a contribution of 1 plus 1, 2 plus 2, and so on. So this set has grown as much as a set possibly can. A plus b will always be equal to b plus a in an abelian group, but other than that, there is no waste. There are no repetitions. Whereas here, can you see why the cardinality of a plus a is 2a minus 1? A volunteer not from the first rank?
It's also arithmetic progression.
Exactly. Because a plus a is going to be 2a plus m, and so on, until 2a plus 2k minus 2. So what can we say? So, I suppose this. So the question then is, when are we in this case and when are we in that case? That is, when do we have that a set grows a lot and when do we have that the set grows very little? So, so what can we say if the set barely grows? So the answer will be A is more or less, I will like an arithmetic progression, like star. So of course we will have to make this statement more precise before it can become a theorem. So let me give some examples that are similar but that are not quite star. So can we think of some examples? So, first of all, if we take any subset A prime of this set A, then clearly A prime plus A prime will be contained in A plus A, which will be less than 2A. So A prime plus A prime will be less than 2A. So let A prime be a subset of A here the condition later. So any subset is going to satisfy A prime plus A prime, so it's equal to A plus A. So what happens now? Well, of course this is less than 2A, but how large is this compared to that? Well, yeah, I mean, well, actually this is less than that, that's what we have shown, but what we really wanted was an inequality relating A prime plus A prime to A prime, not to A. But if we just assume that A prime is fairly big compared to A, so if we assume that A prime is at least epsilon A, then this is just at most 2 epsilon. So the moral is that any large subset, I think fairly dense subset of an arithmetic progression is also going to be a set of relatively small growths. A prime plus A prime will be at most a constant times A prime.
This constant is...
the constant depends on epsilon.
Epsilon.
Yes, okay. It's 2 over epsilon. Yes. Now, we also have that we could have what's called the two-dimensional progression. So this would be another example. So this is not, strictly speaking, an arithmetic progression in its traditional sense. But so this also satisfies, well, it's no longer a 2, it's a 4. And how do you see that? So this is like an arithmetic progression, but two-dimensional, so to speak. There isn't just one modulus m, there are two moduli, m1 and m2. And it's going to have little growth, well, 4 rather than 2, for exactly the same reason as before. So exactly why? Why is a plus a at most 4 times a? Like this. Can you see this?
Yes.
Yes.
It's a sum of 4 arithmetic progressions.
Yeah. So well, it's or it's not even a sum of 4 arithmetic progressions. It's well, it's going to be the same thing, but longer. So it's going to be 2a here, and here it's going to go up to 2k minus 2. And here it's going to go up to 2k minus 2. See?
This k and this k is equal, yes?
Yeah, they don't have to be. But in this case, I could say more generally that they are different. Yes. But I just had this condition so that we would not have any intersections. So, yeah, so a plus a is going to be the same thing, but 2a, 2k1 minus 1, 2k2 minus 2, excuse me. So it's just like here, where we had that a plus a was that. Very well.
One question more. Doesn't matter then this arithmetic progression has no intersection, yeah?
It matters a little bit. The fact that it has no intersections makes it immediate that a plus a is, well, exactly for a minus 3, I think. But if these had intersections, then it would be, so here you can see right away that the size of these is simply k1 times k2, because there are no intersections, and you can also tell exactly what the size of this is. If there were intersections, it would be a bit messier, but you would still have little growth. We will go into that in a second. It's nicer when there are no intersections, but it does not matter very much.
Mm-hmm.
And finally, you can also say that a prime, or a, say, is the union of 3 arithmetic progressions of length a. Then a plus a is at most 9 times, well, it would be like there, 2k minus 1. So this is at most 18a. No? So there has been a factor of 9 introduced, but it's still a constant. So you see, say a were a1 union a2 union a3. So in fact, I think the factor 9 here is too big. Well, just writing it twice so that we can tell what's going on. Well, in fact, it's even better and the same modulus. No? Then what is going to happen? So I think this is really a 6 and this is a 12. What's going to happen is that when you add A1 and A2, it's just as when you added A2 itself the previous time. You just get another arithmetic progression of twice the length. So you get 6 arithmetic progressions now. Yes, and I think that here too I was being a bit inefficient. I think it's just going to be 6 here. Yep, in fact 4. So if this is a disjoint union, of course. If it's not a disjoint union, then you do have a 12. It is also clear. So if I have some things that grow very little and that are compatible with each other in some sense, in this case by having the same m, and I take A to be the union, and I add A to itself, then A plus A is just going to be these combinations. Very well. So do you agree? Well, it turns out that these are basically all the examples. I can give a definition that will cover all of these examples, and then there is a theorem that states that if A grows very little, then your set must be of that sort. So this is essentially a full family of examples. So we say P in an abelian group is a generalized arithmetic progression of length, well, of dimension D. The dimension will be crucial. If P can be written in the form A plus i.e. So P is equal to, it consists of all elements of the form A plus some multiple of M1 plus a multiple of M2 and so on, where these lambda j's, oh sorry, excuse me, lambda j, my apologies. Yes. Very well. For some AMJ. All right. So, and we call it proper. This answers your question. We call it proper if there are no repetitions. Very well. So, and it is easy to see that just by the same argument that we gave before and before, that p plus p is at most 2d times p. No? It's the same argument as before, just with general d rather than 1 or 2. So the theorem that we will start to prove now, and whose proof will continue until next time, let A be finite G abelian. Assume that A plus A is at most CA. Then A is contained in a union of, well, there are several parameters here, but I will just state it with one parameter of at most E O. So O notation everybody is happy with from last time. It means at most a constant times. E of D of C. D of C will be some function proper arithmetic progressions of very well. Yes, so this was first proven. So there have been a succession of proofs with better and better D of C. The lower D of C, the better. No, ideally you would like the D of C to grow slowly with C. Logarithmically, really. That was the ideal. We have not got that far, but we have got a succession of improvements on D of C.
Is J with torsion, maybe? J is a abelian group with torsion, yeah? It can or it does not have to have torsion. It could or could not. It could have, yes, because precisely that's what I'm going to give a brief rundown of the history. The first version of the theorem by Feynman was without torsion. It was only for Z or other groups without torsion. Later versions by Ruja and others had torsion. It's called the theorem of Feynman-Ruja nowadays, not just because Ruja generalized it, but also because the proofs that are nowadays given are descend from Ruja's proof, more than from Feynman's proof, though there are elements of Feynman. Very well. So, some history. What did I do here? So, some history. So the first proof for G, well, Z or in general, G torsion free. Of course, Z is torsion free in particular. This was given a long time ago. Well, he's still alive, and I think the original pronunciation is really Freeman. So this, I forget whether he was in Moscow or St. Petersburg, 1966. So Grigory Freeman. That's how you spell it in Russian, right? Presumably. At any rate, the second proof, yes, so that proof was rather long and few people could follow it, but it's clear now that it's essentially correct. But it was hard to generalize, and it was people had some trouble understanding it. So there was a second proof, rather different, by Rouget, for the same case at first. This was 1994. Then there was also, for some other G's, he also had. So in particular, there is a very simple proof given by Rouget for G of bounded exponent. But then it turns out that it was true for all G, or abelian G at least. So this was first proven by Rouget, and also there's a slightly different proof in Taowu, which is actually slightly later. It's just that the book took less time to be published than the paper. Very well. If you are dealing with an abelian group, general abelian group G, or in general something that is not torsion free, you have to change the definitions, the statement slightly. So it would be progression P plus H subgroup instead of. So there where the statement says a progression, you should replace that by a progression plus a subgroup if you're working with a general group G. In fact, here we will work we will just do the case of torsion-free groups. In particular, we will do G equals to Z. But everything we will do carries over to torsion-free sets, and most of what we do also carries over to the general case, though there are some additional complications. Very well. So, so let me also mention some other names, because the original bounds were not very good. So, but originally, the first bound may not even have been explicit in the case of Riemann, but originally D of C was something like e to the C log C of 1. Very well. And then you had No, excuse me, mistaken. There's no e here. It was just c log c of 1. It may even have been a power of d of c at first. I have to double check that. Then were some further improvements due to Schoen. So he got d of c e of log c. I should also put here. I think there was a further improvement here due to Chang. So I have to make a note. I will give you the notes in Russian for last session are almost ready. If you can give me your emails, I can send them to you by email. But I can also bring them printed out next time. Я буду питать, я питаю заметки для первый урок по-русски, и я буду печатать также заметки для этого урока.
Вы можете вешать их на сайте лаборатории.
Очень хорошо, я буду делать это. Да. Но мой русский мне немножко стыдно. Мы будем делать это. So the best result to date is that of Sanders, who has of log C3 So it's still a conjecture that d of c can be set equal to O of log c. This would be optimal. Simply because it gives a result as good as you could possibly hope for. I mean, you can write down an arithmetic progression of this dimension, and it will have rows c, in fact. All right. Yes, so this would be C of 1 arithmetic progressions of dimension of log C and size. So, and this is, I mean, the O of ones are the O's are the only source of non-optimality, because you can have a union of, say, C arithmetic progressions, and the growth will be C, or rather C squared, ditto for here or that. No? So once we get here, we will not be able to improve things any further, except at the level of, well, you know, what is the degree of the polynomial? That is, what is the constant hiding here? No, so it's not called the logarithmic conjecture, it's called the polynomial conjecture, because it gives you a polynomial here and here. Very well. I should also tell you that there are other versions of the conjecture floating around, but they are all more or less similar. So, for example, we will actually prove this version first and then deduce the version I stated later. But some people actually think that this definition I'm going to give you is more natural. It's when you have Q a convex set and phi a homomorphism. So it would be a homomorphism from R to the D to your group. And so we use cosets in the statement, when you can use cosets of things of the form ZD intersects a convex set So it's what's called the centered convex progression. Instead of generalized arithmetic progressions. All right, so let us go into the proof. So in fact, we will not just do z, because we will actually pass to z mod mz at one point and work most of the time in z mod nz. But before we do that, let me give you some I still have that board to play with, but this will dry. Let me give you some really basic, quote-unquote, additive combinatorics. The name additive combinatorics is quite new. This year is a bit older. So there are the Plunike. So 2 would be basic additive combinatorics. So Plunike-Ruche inequalities. So, well, what are the Plunike-Ruche inequalities? Let me just put this, meaning the same as above. It's the theorem of Plunike-Ruche. Let G be an abelian group. AG, let me call this theorem 2.1.1. AG finite such that A grows slowly. Then, for any KL greater than or equal to very well. So here Ka denotes just so actually part of this is also true for non-abelian groups. A slightly weaker statement is true for non-abelian groups. Because this is telling you that if A already fails to grow the first time, as in A plus A, then even if you add it to itself 100 times, and you subtract it from itself 100 times, or 200 times, you'll still get something fairly small. For a general group that is not necessarily abelian, you don't quite have that. You need a stronger assumption. You need to assume that A plus A plus A is small. And that's actually that half, the half that is true for any group, is actually the easier one to prove. And the basic tool.
The technique of this proof is for non-abelian groups.
Yes.
The technique of proving is the same.
Yes, I will give it to you right now. It's just originally people always assume that things are abelian, or even that G was Z. It's just that then people went and realized, wait, this proof works for any group. So in fact, when I write plus whenever I'm in an additive group, but I will write times when I'm in a general group, but times may be plus, because the group may be abelian. So the proof will rely on the following lemma, which we will write multiplicatively. So let G be a group abelian or non-abelian. So we write times for the group operation. Whereas we usually write plus. So when we use this, we will use it with plus, because we will use it in the abelian context, but I will write it with times because it's true in general. And there are three sets, all finite. Then U times V their inverse is at most written additively U we will go over this funny name. Why is it called? Well, I haven't written it down, so let me write in a triangle inequality. Как это по-русски? Неравенство треугольника. Неравенство треугольника. Не вижу, почему это называется как так. Но first, let us do the proof. The proof will be quite simple. One way that often works in additive combinatorics to prove an inequality is to construct an injection. It's as simple as that. So, or is that? So proof, it's enough to construct an injection sorry, I'm writing things multiplicatively, so it's from here, clearly, because I can put, if I can put something into something else, it's because the first thing is smaller. So how am I going to construct an injection? So for each y fix then define this map, sorry, first wrote the proof multiplicatively. So, excuse me. So for each y, in here, there has to be some way to write it, of course, by definition, as a product of an element of V and an element of W. We fix such a way. We choose it once and for all, and then we set y is equal. So, I mean, you know that y is V of y times W of y inverse. We know that. So then what we do is we define the map as follows. In fact, you can fix what I wrote, which is of course wrong because I first wrote it for the Billian case. So in fact, what we have is this. So this is the map. You take uy to vyu inverse, uw inverse. So clearly this is in big U inverse, big U, big W inverse. Now, so how do we prove that this is an injection? If we can reconstruct the output from the, if you can reconstruct the input from the output, we have an injection, right? So if somebody tells us this, and we can tell what u and y were, we're fine. So we can tell so injection because it's an injection because it has an inverse. It's an injection because we can tell y, which by definition is vy w y inverse, from Vy U inverse and UWY inverse. Why is that? If somebody gives you this and that, how do you figure out this? Somebody? Exactly. You multiply them, so you get back this. And now that you have y, you are allowed to use, you're allowed to work with this, with that, and with y. How do you recover u? How do you get u from y and say v of y u inverse? Or this one? Again, you can multiply. You can tell u, which is u w y inverse times w y, from u w y inverse and y. So this is an invertible transformation, and hence it is an injection. And so you have the inequality. I see несчастье.
What is y? Буковка этого, которая на и похожа, русскую. Вот что это?
Что?
Не, выше.
Да. У. Выше.
Да. Вот, ну, да, вот у это что вообще?
U,
Y.
V, Y, W, Y. Нет?
Правильно отображение звук крест выводит минус первый.
Нет, я знаю, что...
Где?
Что-то... Ну, как... Ну, вот это...
У первые компоненты. Мы по паре у, Y.
Это у...
No, что был проблем?
Okay, no problems.
Каллиграфичный проблем?
Yes.
No, что был каллиграфичный проблем? Я хочу знать.
Я X с U перепутал.
X? Нет X. Очень хорошо. All right, so there's an injection. It's an injection, right? Now, if you apply a transformation to your cat and you manage to get your cat back, it was an injection. So this is true. So it's that simple. Now let me tell you just why it's called the triangle inequality. So we could define we could define this, and then if we define this, then you could, the lemma states that delta, I mean, you can just rewrite it like this. Delta of VW is more than or equal to delta of VU plus delta of UW. So, a triangle inequality. Nierozwiązłość trójkątnika. We will not, so I actually think that this notation is very nice, but we will not actually work with this because this is not a genuine distance function. So delta U to itself is not zero in general. So this is a notion of, so delta for distance, this is a notion of distance that was introduced but did not catch on. To catch on in Russian. It's a notion of distance that was not generally adopted, but because the inequality became so nice in this notation, it became known as nierozwiązłość trójkątnika.
What is the same as the inequality of the left board?
Divide, exercise.
Not plus, but multiply maybe, no?
Oh, log. I forgot. Thank you. Excellent. People are awake. No, it's true.
But now it's maybe...
It's the same one as before with multiply. Yes.
It's
just divide by u squared on both sides, right? I don't want to change this, but if you wish. Or divide by, well. So here would you divide by v u w u. So I have divided by the square root of VW, and I have also divided by U, that's why this disappeared, so you get your inequality. Very simple. So it's very nice, but because it's not really a distant function, we will not be using it. And people don't generally use it. All right. Let me also tell you. So let me give you a little exercise. But since you're quite fast, perhaps you will do right now. Exercise. Prove that for any G, abelian or non-abelian, and a finite, if if this is true, then we do have, well, basically Plunecker-Ruja, though I have stated it a bit differently because it's more general here. It's non-abelian, so not necessarily abelian. So you can have pluses and minuses in any order. You get that any product of A's and its inverses of length k is going to be bounded by c to the O of k. In fact, O of something small like 2. O of k is 2k or so. Or 3 perhaps in some places. All right, so this is an exercise. You can do it at home, but it's not difficult. Or you can do it now if you wish, but the idea is basically that you start plugging in V and W and U are going to be sometimes A squared, and so on. And so you'll get a shorter product here in terms of, you'll get a longer product. V and W will be longer in terms of two shorter products. That's a general idea. But you can do it. let me just tell you what is the difference between this and the abelian case. If we assume only AA is equal to CA and not, we are not assuming that AAA is at most CA, we need G to be abelian to conclude anything.
Do you know a counterexample?
Yes, I'm going to give you a counterexample right now. Even, you know, even just for three products, you cannot conclude this, and I will show you why not. So we can have, and this happens in many groups, not in all. G non-abelian. If G is non-abelian, it can be the case that there is a subgroup. Notation for subgroup is fine. Subgroup. And some conjugate such that they intersect only at the identity. It can happen. It happens a lot of the time. So, quite common. I can give you a specific example if you wish. You could have, for instance, G could be the symmetric group. H could be, you know, powers of the n cycle. And tau could just be a just transposition 1, 2. Is this notation clear? Or if you don't know what this is, it doesn't matter. Because any group that's any subgroup where you can have, it also happens in linear algebraic groups a lot. Because if you say that this is H and you conjugate it and it becomes this, then and in such a way that they are transversal, then they intersect only at the origin. That's what being transversal is. In that case, what do you mean? What do you have? You will have then we'll have that h tau h h squared. Why? A tiny exercise. It's the case. When you have h like that, this is the case. And so, for a equal to h intersection tau, we have that AA, on the one hand, this is going to be less than 3a. It's very simple, because a times a will be h times h, which is just h times tau, tau times h, and then just tau. So this is not strict. Yet on the other hand, what will we have? AAA will contain in particular, containment implies an inequality, so AAA contains HTH, so it's at least h tau h, but as we said, this is h squared, so this is a, which is really large, so this is small, really small, the constant is 3, Yeah, this is huge. This is not a constant square or a constant times a billion times a, it's much larger. So I hope this answers your question. Yes. But we will see that in the abelian case, you don't have this sort of situation. I mean, in the abelian case, of course, this example does not work because your conjugate is always yourself. And yeah, we will see now that you can prove the Kronecker-Rouget theorem in the abelian case just starting from a plus a smaller than c times a. And it turns out to be quite subtle. The proof used to be long, but nowadays it's much shorter, and that's a very recent development. That's from 2011 by Petridis, who was finishing his PhD at the time. He simplified existing proofs a great deal. So I will write things with plus and minus. I will write things in the abelian way. And there has to be some place, because of the counterexample, there has to be some place where we use the fact that G is abelian. But goodness knows where it is. So it will be very good to know. So let G be abelian. But is this really necessary for this lemma? I don't know. So this is a key proposition in Petridis. 2011, such that then for every in G for every subset of S of G, we will have this is a very general statement that A plus B. No, so the idea is always to be able to bound a longer sum in terms of a shorter sum. Given as an input, mostly just that A plus B is less than or equal to Ki. Actually, if we just had this condition, as we are about to see, we would not be able to conclude this right away. So people were stuck. But we can add this condition, which tells you, in fact, let me put equal here. So for every, yes. So this is telling you that, in fact, A is in some sense optimal. That all the subsets of A make B grow more with respect to when you get B added to that. And we will be able to apply this just by choosing a minimal set or a pessimal set in some set, or optimal if you wish, in some way. But there are these conditions here. And we will see how the second condition is useful. So that was the writing idea of Petridis. Before, people were just proceeding like this, and they were unable to get something like that easily. So the proof is by induction on S, on the size of S. So base case is when S has one element. And this is trivial. You just do it. If S has one case, you have that A plus B plus S of size A plus B. You are just shifting the set. And that, by assumption, is K times A. So you are done. So is the terminology clear? Base case and inductive step? Jak je to po rusku? W osnowie bazy indukcji
i indukcyjny переход.
Индукционный переход, да. Очень хорошо. So induction case. So we assume we have already done the case for all S of size so where is in N. And X is not in S. So the first attempt A plus B plus S prime. So we're trying to control this. So we're trying to prove this for S prime. So we go and, happily write this is at most this. Clearly the case because this is the union of that and that. And by assumption, this is K A plus S plus A plus X. No, I mean, this is the same as A plus B, which is at most size A, which is size is the same as that of A plus X. It's clear that the size of A is the same as the size of A plus X, right? We are just displacing a set, so its number of elements does not change. Well, so we're using here, we're using this 1 star, and here we're using the fact that we have already proven the theorems for sets of size at most 10. So we are here, but then, we are a bit stuck, because we would like to conclude that this is yeah, so we would like to get done here, but we are not done. We would like to conclude that this is this at most A plus S union X. So it looks like we're almost done, right? But are we? No, we are not almost done, unfortunately, because when the sets are, if these two sets are disjoint, then this is true. You see, this set is a union of these two. But what happens if these two sets are not disjoint? If these sets перекрываются, then the sum of the number of elements is bigger than the size of the union. That's not good, because this will be in the wrong direction. This will be like this. So this is a first attempt. It doesn't work. Here you get stuck. So only this works only if a disjoint. So we can replace our first inequality in 1 star by what? No, not in 1 star, but we can replace the first inequality in this argument by the following inequality with less waste. Or what is set? Z you see, Z is a set of all, is a subset of A, a set of all little a's in big A's, such that A plus X is contained in A plus S. So why I'm able to assert this? Because, so by this I mean the set minus. This is clear. So it's this set minus the elements of without the elements of this set. That is the sensation clear? So it's this set, and I take out the elements of that. So why is this true? It's because I don't need these elements, z plus b plus x, because all of those elements of z plus b plus x are already contained in here. So in fact, you know, I can. This is an equality as cardinalities because this is a disjoint union of sets. So yeah, so you know, this is the set of all anything in here is an A, such that A plus X is already contained in A plus S.
And this you
exactly.
Use the abelian group.
Ah, is it here we are using abelianness?
A plus S plus B, it's not equal A plus
Ah, exactly. Okay, thank you. Ah, I once knew this, but I'm, you know, I went to bed and I forgot everything. But great, thank you very much. Yeah. In this passage. Cool. All right. So we now have A plus B plus S prime is at most A plus B plus S plus A plus B minus Z plus B, and this at most A plus B plus S all right, and here we're happy. So here we are using this assumption, star star, important. So as to get, you see, this is an inequality in the right direction because we have an inequality like that. That's where it comes in useful. And so, by 1 star on the inductive hypothesis, ipotesa induzione pripolegenie. Induzione pripolegenie, we get again, so this one, A plus B plus S is at most that by the induzione pripolegenie, and A plus B is at most K times A by 1 star, by the main assumption. All right, but by the definition of Z, we have that A plus A plus A minus Z is just A plus S prime. No, you see? Because S prime is, remember, S union little x. So you have already A plus S, and then you have to add to that all the elements of the form little a plus little x, which are not already here. So it's all of the elements in A, except for those for which A plus x are already in A plus S. And those elements are precisely these ones. All right. So now, armed with Petridis, we can prove Plunker-Ruja. Let B be such that B plus B is at most C times B. So let K be the minimum growth that you get, you know, in the statement of the theorem, if you remember, I had A, but it's nicer to the proof with B, so it's a nicer letter, so I will use B here. So I will just, I mean, how do I find the right Z? I just find the right Z by the right set A. I just find a set A to which to apply the lemma just by taking the minimum overall Z. Oh, I could. It's better if I write A here, in fact, and let A be the set at which K is at A. Or, you know, A set, because there could be more than one. So it's a non-empty set containing B for which this ratio is minimal. Fair enough. So immediately you're going to be able to apply Petrides, right? Because it does satisfy, well, that for with K by definition, and it's also the minimal thing. So all the smaller sets will be at least as bad. Oh, then 1 star, 2 stars, Petrides. Hold. So, for any K bigger than 1, what do we have? A plus KB note that K is at most the constant C in our, where did it go? Yes, in the statement of the theorem we had, the assumption was that, so in the statement of the theorem C was just A plus B, or really B plus B divided by B. So K is clear, it's a minimum, so we're going to A equals to B is one of the cases, so clearly K is less than or equal to C. So remember, just the assumption was that this was C. Yes. So that was the assumption, so K is at most C, and of course A is at most B. So here we're applying Petrides' lemma, and then we're proposition, and then we're iterating. And as I said, Petrides' lemma is useful because it allows us to make a longer sum into a shorter sum. It allows us to bound a longer sum in terms of a shorter one. So we're almost done. So by the triangle inequality, A KB minus LB is going to be at most A plus KB A plus LB. It's just however you write it. You're just writing the abelian case, but the way I wrote it, it would be U equal to A, V equal to minus LB, and W is equal to minus KB in the triangle inequality, but that's just a matter of letter choice. So you have that, and so by what we said here, this is KKB, KL, no, KLA, So this is what we say, but now we are going to use these two trivial inequalities. So we get Ck plus L A B. And now we divide by A on both sides. And we get Kb minus Lb is at most Ck plus L. And that's the end of the proof. So it's really quite simple. It's tricky. It took people many years to come up with such a simple proof. Before it was much longer, but here it is. So now we have the Kronecker-Rouge inequality. Let us also now, this is in the tradition of Rouge. Let us introduce something that remains from the original proof of Feynman, what's called the Feynman homomorphism and a Feynman isomorphism. La 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 la. So you see, it's really quite nice. In the abelian case, it's enough to know that b plus b is at most c times b for us to be able full control on all copies like that. So it is the use of the Feynman homomorphisms, for instance, that will allow us to pass two definite settings, Z mod and Z. Is there a faster way to clean the board? Oh, never mind.
Just put this dry.
Yes, I'll do that in the future, I think. Yes. So from Z to Z and Z. So section 2.2, Feynman homomorphisms. So definition. Let G and G prime be abelian groups. For us, they will be abelian. In principle, one should be able to define something similar. In general, A is a subset of G. So equal to 1. So we say that a map phi, not on all of G, but just on A, is a, sometimes we will meet the name, Feynman homomorphism of order K, or simply, omitting even the name, K homomorphism, if for all x1, x2 up to x2k in A, such that x1 plus x2 plus xk very well. if whenever we have an equality, we have phi of x1 of xk plus 1 all right. So this is actually related to a concept some of you may have seen, it doesn't matter, called local homomorphisms in group theory, or the theory of in geometric group theory, say. Where we don't have a homomorphism in the entire thing, but we have a homomorphism in a set, typically finite, A. A homomorphism, namely the basic rule is does hold, this basic rule at least. Yes, what else? We say phi is a Freiman K isomorphism if, in addition, meaning also, phi is a bijection, so yes, so phi is injective, and the inverse of phi from phi A to A, of course G, is also a K Freiman K homomorphism. Note no, I'm going to say so I write it. So this just what I was saying, that this is related to so-called local homomorphisms. But this appeared independently in the work of Freiman earlier. Very well. So an exercise, two exercises. If P is a generalized arithmetic progression of dimension d, and phi is a Freiman K isomorphism, then of dimension d. So a Freiman isomorphism preserves arithmetic progressions or sense progressions to progressions, and also preserves the dimension and the size and so on. And it obviously preserves the size because it's a bijection. B. Just a little thing, many like this. If A of k is a Freiman K isomorphism for k greater than or equal to 4, then A plus A is equal to phi of A plus phi of A. No, so obviously A is equal to the size of A is equal to the size of phi of A because phi is injective, but moreover you have that A plus A, the size of A plus A is equal to the size of phi of A plus phi of A. That's just an exercise. You actually do need k greater than or equal to 4, not 2. Very well. Now, I will show you how the notion of a Feynman homomorphism was used by Rouja to reduce the case of the theorem over Z to the case over Z mod NZ, where moreover n is an integer that is not very large compared to A, just a little bit larger than A. That's important, in fact. Let A be a subset such that, and this is the first time that we're actually going to use the fact that we're in Z. What I'm about to write is also true in general of torsion-free groups in some way, but in fact the general case is trickier. Say n bigger than c to the 2k times a, there exists a Feynman k isomorphism, not from all of a, but from a prime to z mod nz for some large subset a prime. Very well. So this is important. It's a so-called case of good modeling. It's a technical term. So as I said, it is true for Z. It's not true for every group. So I actually do mean Z here. Very well. So as we're going to see, it's not too hard, but proof. So let Z, so we have a reduction, and then to some Z must be Z, and then you will have a multiplication, as we shall see. We will have then, here it is a lifting, in fact, and here finally it's a reduction. So it will be a funny sort of map. All of these maps will be the natural ones, except for the magical map psi 2. So what is this magical map? So, I might as well write it here. So, psi 1 is reduction mod p. This will be chosen later. Psi 2 is multiplication by q. So, p will be chosen once and for all, but q is really the thing that varies, and because we will be able to choose a q that makes things work. And in fact, pretty much a random q will work, or many q's will work, but a typical q will work. Phi 3 is a slightly phony map, if you wish. Как phony по-русски? Нечестливый. Phony. Somewhere between fake and dishonest. Well, you see, this is not a very honest map, but it exists. So it's the map that takes, in fact, these to the 0, 1, in the obvious way. Obvious, but phony way, yes. And psi 4 is a reduction mod p. No, mod m, sorry. N. And we define, so these are map psi. So psi is defined to be, of course, psi 4 Very well. And hence, they are in particular homomorphisms. So all of these are homomorphisms, all the maps except for our phony friend. Dishonest по-русски?
Нечестный.
Нечестный. Наш нечестный друг, C3, which will not be an honest homomorphism, but on an interval it is a homomorphism, a k-homomorphism. So you see, this is a k-homomorphism for any interval of length about p over q, p over k. Why is that? In general, if you just let it be over, if you do not restrict it, then it would not be a k-homomorphism, because, you know, if you add p minus 2 and p minus 1, you get back p minus 3, or, you know, if you just sum p over 2 plus 1 and p over 2 plus 1, you get something with a much smaller reduction, so it will not work like a homomorphism at all. But if you restrict to an interval, then it is a homomorphism, because the only way that the images, the only way that you will have, you're not going to get any rounding errors, basically. This is actually easier to understand than to explain. First of all, do you see it for j equals 1? For j equals 1, it's clear, right? Do we agree? So everybody understands what this map is, right? Now, if you restrict to the first, the chunk at the beginning, from 0 up to p over k, it's a k homomorphism. Yes, because there's no reduction, right? Oh, C1 is reduction mod p. Как reduction по-русски? Редукция? Редукция. Это мультипликация mod на q. Psi4 это также редукция mod n.
And what is Psi3?
Psi3 it's this map that just takes, so it takes 0 to 0, 1 to 1, 2 to 2, and up to p minus 1 to p minus 1. But of course, it's a reduction map. It's when you, and of course it takes p to 0, p plus 1 to 1, and so on. It's the modulus map. I mean, it's what we believe modulus to mean when we are in secondary school.
And what is small q?
Small q, we will choose small q later, however we wish.
Is it a small q prime or not?
Small q need not be prime. P needs to be prime. Q can be whatever it wants to be. All right, so the modulus map, let us call it the modulus map, Psi3. So it's the dishonest modulus. Because modulus is really the reduction, but, you know. The dishonest modulus is a k-homomorphism on the first interval. And it's also a k-homomorphism on any interval of this form. Why? Because phi of x1 plus so this will always be something of this form. So it will live in Z. So this will always be basically j minus 1 plus, so it will always be contained. So if you have that two sums of this form are equal modulo p, then basically, so x1 plus, so if, so this will be j minus 1 to phi of x1 plus, that's why. So you can write it this way. So it's clear that if you have any k elements that add up to the same thing,
now C3 is a homomorphism, but this composition.
so sorry, C3. It's C3. Sorry. Okay. And this gives you the same thing. Say 3. Are people convinced now? So it's a k homomorphism, you see, by definition. If when this is equal to that, that's the assumption. When this sum is equal to that sum, then this is equal to that. Everybody happy now? All right. So what do we do? We're just going to choose. So there are k intervals like that, and we choose the one which contains the most elements of A. And yes, a composition of k homomorphisms is a k homomorphism. Very good.
Question about composition in formulation. The case k equal to because it's the best. No, because what was the difference for different k?
For the homomorphism, or
no, in this proposition which you clean now.
Oh, you mean little k?
Yes.
Yeah, I forgot what I cleaned. That's a problem always, isn't it? You mean not? No, there's no k here. You mean
no?
Yeah, Plonica Ruja.
Yes.
This one? No. Which one?
No, the last proposition.
I'm really confused. What was the last thing that I defined what a Feynman homomorphism was?
Yes. This position because k equal 2 is.
Yes. No, but it's stronger to be three isomorphism than to be yeah. So of course it's better if A prime is the better A prime is the better. But you see, if being able to construct a 10 isomorphism is a much stronger conclusion.
It's a
Isomorphism.
Yeah,
Yes.
okay.
Thank you. Just as. Oops. All right. Where were we? All right. So we choose. So. By pigeonhole, which here gets called Dirichlet, but it's, I think Dirichlet would be embarrassed to be remembered by this. So there is an ij such that aj, which is defined to be sort of how x is in A So we just choose the interval that is richest, the interval that contains the most images of A.
We didn't fix Q yet.
I haven't fixed Q yet. I haven't even fixed P, though P doesn't much matter. It will just have to be big enough. Yeah. Very good. So P is pretty much arbitrary. P is in really any prime big enough for the map to be injective. Very well. Okay. We haven't chosen Q. I will just show you that there exists a Q for which things work out. So we do have that Aj to Z minus Mz is a Nz is a K homomorphism because it is a composition of a lot of K homomorphisms. Most all of them except one, they are honest homomorphisms. So it remains to show that it is a K isomorphism. We must show it is a K isomorphism. For this, it's actually enough to show how much time have we got left? I think, can I get to the bottom of the page? Сколько времени? Implies, so this of course half the conclusion, but it actually implies injectivity. It's a difficult part. The other part is injectivity, but this implies injectivity. Why? If psi of x equals psi of x prime, just take x 1 xk equal to x, and then you do it, and here you use the fact that z is torsion free. Yes. So all we have to show is this. Now, how could this, suppose that these were false. Then there is some set of elements for which it fails. So it's some elements such that this expression is non-zero. Very well. But what does this mean? This means that QS mod P, so QS mod P is just, you apply psi1, then psi2, that is, psi1 was mod P, then you multiply it by Q mod P, and now you're going to apply psi3. So what will happen here is that this will be a multiple of n. No? Because only then do you have that it's going to be reduced to 0 by the last step. But how many ways are there in which this is possible? Well, the funny thing is that S and the multiple of n determine Q. No? Once you know what, you see, psi 3 is injective. It may not be honest, but it's injective. So once you know your multiple of n, you know what QS mod P is. And if you also know what S is, then that determines Q. So how many bad Qs are there? That's the question. How many, well, how many S? The possibilities are Ka minus Ka possibilities. No more than that, because you are talking about S's of this form. And then the second question is, how many multiples of n there are just, so there are at most p minus 1 over n multiples of n in, 1 up to p minus 1. It's going to be 0, so all right. So because of that, the number of bad Qs is at most p minus 1 over m times Ka minus Ka, and it's only here that we finally use Pluneke. So it's at most p minus 1 over m c to Ka by Pluneke. And so, since m, as we said, was bigger than c to a 2 Ka, this is smaller than p minus 1. So there are fewer than p minus 1 possible values, bad values of Q, yet there are p minus 1 possible values of Q, so there's at least one good Q. In fact, there will probably be a lot, but there's at least one Q. So this is good. We choose that Q. And set A prime equal to 8A. And that's it. End of the proof. So you see, in all of this game, Q acted as the role of a scrambler. The point is that you're going to fail. So Q, it's a very simple way to make things a bit random. A very simple way. And the point is that when you scramble things a little, coincidences become unlikely. So the moral of the proof here is that just by choosing Q pretty much arbitrarily, you get that it's going to be a prime and K homomorphism unless something unlikely happens, and just by taking out all the exceptions, the bad cases, you get that there is at least one good case. In fact, for larger m, there will be a lot and a lot of good cases, and so you are done. It's a philosophy. But the point is that there is a Feynman-K homomorphism from Z to Z and Z. And as I said before, all of these properties of growth and of being a progression are preserved by the passage to Z mod n Z. So we will be able to work in Z mod n Z. But that will be next time.